So, welcome to the very last talk of the workshop. So, Pal Schenck is going to send us out with a bang, I assume.
Optimism is good if you're a mathematician.
With a talk about oscillators and computational algebraic geometry.
Thanks. So let me start off, since this is the last talk, it's of course the duty of the last speaker to thank the organizers, so I think we should all give the organizers of the workshop and the program here a hand. And so, the game plan for the talk is over here. So there's going to be two pieces. The first piece is background on oscillators, because a year ago, if you said, tell me about what an oscillator is and what the questions are, I would have been clueless. And I remember Beth in her talk said, so some of you are going to zone out, and that was in reference to the p-adics. So probably if I went to a colloquium talk and oscillators was in the title, I would be sitting in a back corner and very surreptitiously opening my laptop. So, so the first half is the applied aspect. The second half will do some.
I did that in the front.
Yeah. Well, Frank, you're an exception. So the second half will be the computational aspects, and we'll flavor our meal with just a dash of toric geometry and a tiny pinch at the end of group actions, because group actions are here. So the other thing I'm going to say is, when I was a kid, I loved the Dune books, and in the Dune books there's a tribe of freemen, and the freemen live a pretty ascetic existence, and they have a slogan which is "Be prepared to appreciate what you meet." And for me, be prepared to appreciate what you meet. And so for me, the appreciate what you meet is these blackboards. And so if my writing becomes illegible, the paper's on the archive, but there's also slides on the I&I website. So I decided to change and do a chalk talk based on all the wonderful chalk talks that have been here. So, but there's a trapdoor into the talk there. All right. So the first question is, oh, I lost my video here. So they say you can't teach an old dog new tricks. I have never. Why didn't it play? Play. There we go. I've never started a talk. I've never had a YouTube video and a talk, but apparently old dogs can learn new tricks. So these are oscillators. This is a sequence, a bunch of coupled oscillators. This is kind of a bunch of mathematicians, like when you're running a committee meeting and you want, the mathematicians to work together. This is us, right? This is our community. At least the beginning of it. So, and again, this is a metaphor for mathematics. You can see most people are in sync over here, but there's this one problem child over here at the end. It's probably me. But slowly, and this is not mathematics, the majority brings the outlier into sync. All right, so that's enough for the video. So that's what we're interested in. This is a system of coupled oscillators, and okay, so that's what we're interested in, is coupled oscillators. Why do we care about oscillators? So oscillators are ubiquitous in science, so they appear in things like chemical networks, biological networks. I should have said, this is joint work with Heather Harrington and Mike Stillman. Heather does a lot of applied math, including neuroscience, so oscillators appear in neuroscience, but also in more pedestrian applications such as power grids or communications networks. So, so there's a lot of interest in oscillators, so that's sort of the who cares about oscillators. So I'm going to talk about a very specific model. So this is we're now ready to start introducing our dramatis persona. So this is the Kuramoto model. Happily, this is like a 50th birthday talk. So 1974. So Kuramoto introduced the following system of differential equations. So what this system of oscillators is going to be is a system of first order differential equations, and they're going to be trigonometric. So the model is the following. And our underlying data structure.
Are whose oscillator related to the video you showed us?
Pardon?
Are whose oscillator related to the video?
Absolutely. So what that was, I had five, what we're going to think of as our underlying model is a graph. It's not a complete graph. That was a complete graph because every one of those 5 oscillators was being influenced by the other ones. But typically, what you're going to have in a network of oscillators is the underlying structure, underlying data structure is just a graph, and this is going to be a simple graph, simple and connected. So no loops, no multiple edges, and it's connected because if you've got a network that's separate, it just behaves on its own, right? So there's nothing interesting going on there. And so at each vertex, the vertex is where my oscillator is going to be, and you want to think of that oscillator as transmitting some periodic signal. It's a flashing light or something, and because it's periodic, what Kuramoto is going to model that with is theta I is the angle at vertex I, and the differential equations are theta sub I, let's say this is on, and v sub, cardinality of v sub g. The number of vertices is going to be n for me, so when I write n if I've forgotten, that's the number of vertices. Theta sub I is equal to omega I plus k times summation vj vi is in the edge set of g of sine of theta j minus theta I. So I have one such equation at each vertex. A vertex is influenced by the behavior of the vertices adjacent to it, right? So this is the model. And so what are the other variables here? These are the angles at vertex. This is the angle at the vertex. Those are functions of time. So each of these thetas is a function of time. The omega I is what's called the natural frequency. So if you had a tuning fork and you hit it, it will vibrate at a certain frequency. The natural frequency is the frequency it oscillates at when it's perturbed from a ground state. This K is the strength of the connection. So you could imagine in a communications network that if there's a large distance between your nodes, that maybe the communication gets weaker, and of course some nodes can't even see each other. So the most popular variant of Kuramoto's model, actually I should say one other thing, this goes back to the who cares thing. So if you Google Kuramoto model when you're bored, if you've got your laptop open, you get about 6 million hits, at least I did this morning, and in fact, of course Google overestimates the importance of everything, so if you go to MathSciNet and just look how many papers have Kuramoto model in the title, there's over 1,000. So of course that's not a good metric to say, well, it's interesting to other people, so it should be interesting to us. But it's been studied for over 50 years.
It was explained to me once that the people who are interested in power flow equations in electrical engineering are larger than say the mathematical community.
I would certainly believe that.
But it's really
Okay, so the most popular variant of this, so we're going to simplify. This seems pretty simple on its face, but in fact, the homogeneous model, put it up here, homogeneous model.
Just one more thing, I mean, K doesn't depend on I?
No, the typical, well, you could certainly do that if you want. Yeah, so let's even add that. So K is going to depend on I. So the homogeneous model, we first off assume that all of our oscillators are exactly the same, so that the natural frequencies are the same, and that allows us to dispense with the natural frequency piece. And then going to Eveline's question, the other piece of simplification is that the assumption is that the strengths are all the same. So this we set to 1. So this is the model that we're going to be studying, and even though it seems pretty innocuous, as I said, it's the model that is most studied. Okay, so here I cheated a little because well, I had to cheat. So we should have an example. So here's the running example that we're going to use. Again, this is what's cool about this example is this is already a pretty simple graph, right? I've got 5 nodes, 6 edges. And the system of differential equations is exactly written down here, so I'll just do one of them. So at theta 0, my vertices that are adjacent are theta 2, theta 3, theta 4, and so my equation is theta 0 prime is equal to sine theta 2 minus theta 0 plus sine theta 3 minus theta 0 plus sine theta 4 minus theta 0, right? And similarly the rest of the way out. And if you're wondering why I've written this way, written the board this way, it's because we're going to reuse this later. Okay, so that's it. Put that up there. All right, so let's introduce our dramatis persona. Okay, so So the other thing I should say, so here's like sort of the grandfatherly avuncular advice to grad students and postdocs. First off, I mentioned there will be Burns prizes, so there will be 3 whiskey prizes. So there will be questions asked. For the grad, they'll be open to faculty
Is that a
members.
bottle?
Huh?
Is it a bottle?
No, it's not a bottle. I just took shots. Okay, Frank. Frank will offer that. Frank is going to actually. I'm going to leverage my friendship with Frank to have. I will give you a shot and ask Frank for the bottle. All right. So there'll be questions asked, but the avuncular advice was, even if somehow a talk seems like this is not interesting to me, very soon we'll be translating into a question in algebraic geometry. And Simon said. Simon, what did you say during your talk? This is a happy Friday. This is a happy, easy Friday talk. So this is supposed to be a happy, easy Friday afternoon, last talk of the conference, right after lunch talk. So the level of sophistication is not too high, but before we get there, I have to introduce some definitions from dynamical systems. So here's what we've got. So the players are the following. So first off, I'm going to call P equals some theta 0 star through theta sub n minus 1 star is an equilibrium. Can you guys in back see okay? Am I writing large enough? Or we'll call it a solution if it solves our system star with all the theta I prime equal to 0. So we set the theta I primes equal to 0. We find some set of the angles that satisfies that set of equations. So this is called an equilibrium. So this is, now there's some obvious things called standard solutions. Or, I don't know, they're called standard solutions in the literature. These are the trivial solutions. So if theta I star minus theta j star is either 0 or pi for all I, well, of course, then those signs all vanish and you get nothing, right? So that's not interesting. These are standard solutions. There's one of them that's called, that's actually kind of special, which is called the all in phase solution. And that's when the theta I star are all equal. Okay, so, and in particular, if actually a solution is stable, if there exists some delta greater than 0, such that for all q in some small neighborhood of P, Q, the solution Q converges back to P, and with the assumption that P is a solution. So this is the first thing that maybe requires a little explanation, but what you should think of is that I found a solution to this system of differential equations, and then I take the dynamical systems people call this the sink or a basin, and so if I take a point that's very close, as I evolve my system forward in time, this solution gets sucked into so this is like a tiny black hole, so it's attracting solutions to it. So that's a stable solution, and then the stuff that we're going to be most interested in is P is linearly stable. If the Jacobian of the Kuramoto system, I should name that thing. This is going to be called star because it's the star at the top. If the Jacobian of star is negative, semi-definite, with only 1, 0 eigenvalue. And so I apologize, I got one last thing to put up here. So these are going to be, and when I state what the questions are that are of interest to the dynamical systems community, I need some terminology. So this is sort of the language that we're going to be using. And then we say that a system star synchronizes if the only stable solution is the all-in state. So that was what the video showed. The video showed all of our oscillators were marching to the same beat, right? And so this is a question about the synchronization is when that happens. So those are the players and the definitions that we're going to be interested in.
Can you comment on the zero eigenvalue? Is there always a zero?
Yes, there will. There's always going to be zero eigenvalue, and it's basically going to be because this matrix is always going to have at most rank n minus 1. Yes, question. Wait, in back and then Jordy.
Oh, so that's because of the vertex of Boston, probably because of the edges.
Oh, damn it! You can't win a prize. All right, grad students should cover their ears, right? Yeah. So, Jordy.
So these stable solutions correspond to in chemical reaction networks to steady states. Is that?
That's right. Yeah. Okay.
Dynamical system, yeah.
So those are the players, and so now let's see. Now I want to talk about. I think we've got at least all the terminology down. Yeah. And then, I did want to say one last thing. So actually two little asides here. So the first aside is about the linear stability. And roughly speaking, what's happening here is what we teach our students in vector calculus, calculus 3, which is when they do the Hessian test to look at a surface. If the determinant of the Hessian is positive, then they know it's a max or a min. If it's negative, they know they're at a saddle point. And if it's 0, they don't know what's going on, right? And so the idea here is that if this Jacobian has too many zeros, we're going to have to do not just linear analysis. We won't have to just look at the Jacobian. We'd have to look at higher ordered derivatives to figure out what's happening. And this is exactly, it's a loose analogy, but not so loose. It's really almost exactly what's happening here, is that this is essentially sort of looking at the simplest kind of test to see if we've got a stable solution.
So is it that it's negative and the other direction is away from this eigenvalue? That means you flow back.
That's exactly right.
That's the consequence.
So and the reason I said that is I wanted to say linearly stable implies stable, but the converse is not true. Exactly for this reason that I said, that you might have some 0 eigenvalues, but you just don't know whether it's a min or max. So that was step 1. That was remark 1. There's a second remark I want to make here, which is for just in case. We have a remote audience too, right, in Ibadan or not? Okay, so just in case somebody really is sort of a dynamical systems expert, this system is what's called a dissipative system. And so what that means is that it's sort of the nicest type system that you can have. A lot of times we see, so this means there's no limit cycles. You can't see that in the back. No limit cycles. And no chaos. And I'm going to say very briefly what those two things are. So if you ever watch dynamical systems animations, a lot of times you see some little particle that's floating around out there, and then it starts to orbit something, right? So that's a limit cycle, is a positive. Yes, question?
Say not for the implication down.
Yeah, I said it, I just didn't write it. But you should get, you know what? Anybody who catches me with a mistake gets a shot of whiskey too. So no limit. There's no limit cycles. Yeah, did you get one?
Do you mean all in phase solution and not all in?
All right, that's 2 whiskeys. Well done.
You didn't make it.
Well done.
To the store after that.
Well, I'm going to drink with you guys, so it's all good. And no chaos. So chaos. Again, I'm going to be a little bit cavalier. So the idea of chaos is the butterfly effect, which means that your system is very sensitive to initial perturbations. The usual analogy people use is a butterfly flaps its wings in Osaka, and there's a tornado in Cambridge or something like that, right? So there's no limit cycles and no chaos. So this is and again, because it's dissipative, so dissipative essentially means there's leakage and that things are going to stabilize. And the stupid analogy there is, if you took a little model car track and you put your car up here, you've got potential energy plus kinetic, starts moving down, your potential energy drops, kinetic increases, goes back, but it doesn't go back and forth forever because you're losing energy through friction, right? So your dissipative exactly means that the system is going to stabilize. So this is a really, really nice system, and yet there's lots of open questions about it. Like I said, like 1,000 papers written on it. Okay, so we're now done with that, and I want to talk about the questions that are interesting and history. So questions in history. So questions, and the questions are actually about dynamical systems in general. So questions. When does a system, any system, synchronize? So when does a system synchronize? When does it have stable solutions? When does it have linearly stable solutions? So now so that's the questions, and now I need to do some history. So this is problematic because, HSTORY, it's problematic because there's over 1,000 papers on Kuramoto models, and I'm gonna put down maybe 6 or 8 signature results. And again, what is a signature result for me is probably not a good indication of what is a signature result for the folks in the field. So 1994, Strogatz and Watanabe showed that KN, complete graph, stabilizes, syncs. Moving along, 2006, Strogatz again, Wiley. And the convention I'm using is the way that the authors are listed on the paper. We're very egalitarian in pure math, but the applied maths maybe not so much. Wiley, Strogatz, and and showed that circulant graphs have linear, not in phase solutions. And I'm going to actually give these a name. Linear, not in phase solutions. I'm going to call the ones that we're interested in, I'm going to call these exotic. Or we call these exotic solutions. Circular graphs have exotic solutions. 2012, Taylor showed that if the connectivity of the graph, which is by definition the minimum degree of a vertex, so the minimum degree of a vertex is just the number of edges coming into it, divided by the number of vertices minus 1, so that's connectivity. If mu g is greater than 0.94, you sync. Followed by 2015 two results. And I'm going to put 2 other ones down here. Yeah, 2018, 2015, Canal, Monzon show that there's graphs with about connectivity about 0.68, which have exotic solutions. 2015, there's a result of Meta, DeLeo, Dorfler, and one other person that I'm going to leave off for a second. 2018, this is Ling, Zhu, Bandiera. Much improved Taylor's bound showed that if mu is greater than or equal to 0.7889, you sync. And the last result that I want to put up is to indicate that even small improvements are interesting. This is a result of Liu and Steinerberger. If mu is greater than or equal to, I want to get this, I want to put it down right, so let me find it. 7929. Ha, nobody got me. You should have yelled when as soon as I said I got to correct it. That would have been a bonus. So 7929, 7889 sync. All right, so there's I've done my Sting says history will teach us nothing, but there's our history, brief history. And so the question, here's a whiskey prize, open to anybody. Where's the algebraic geometry? Where's the algebraic geometry? Yeah, Frank.
Yours said torque geometry.
No. Too specific. Not that's like part of the phrase.
Well, I mean, you know, sine is an algebraic function.
Thank you. Okay, so Frank has solved the puzzle. So the point is, of course, that sine of theta j minus theta I is just sine theta j cosine theta I minus sine theta I cosine theta j. So, so we are going to relabel things as yj xi minus yi xj's. The name that I left here, which was supposed to keep you from thinking about it, was this is John Hauenstein.
I see.
So this is the first.
You embedded that as a circle as opposed to the C star.
Exactly. So these are the first people to start. They used numerical algebraic geometry to study Kuramoto system, the Kuramoto model. So that's the first intrusion of algebraic geometry into the Kuramoto model. So the point is now, what do we have? So we have well, we have our equations. We have n equations that are just xi squared plus yi squared minus 1 equals 0, right? So I have n of those. And then I have n other equations that we'll get when we translate our signs, these equations into xi's and y's. But first, before we do that translation, so that's where we're going, is the algebraic geometry. But I missed an opportunity for someone to win a whiskey prize. So the whiskey prize was to say, let's take a look at this system and look at the Jacobian of this at the, I mean, we should always, you know, like we tell our students, benchmark with a simple case. So let's benchmark at this all-in-phase solution and see what happens to our Jacobian. So we're going to take the Jacobian of this system. So when we take the Jacobian, it's pretty nice, right? Because when I differentiate these things, let's let this be partial 0 here, partial 1, partial 2, partial 3, partial 4. This is not related yet to the diagram. I'm making an n by n matrix. The point is, when I differentiate this first equation with respect to theta 2, this is just going to turn into a cosine. Everything else vanishes. Theta 3, everything vanishes but this. This becomes a cosine. Everything vanishes but that. That's a cosine. But I also have an entry over here for theta 0, and this is just, I'm going to write star, and star, little star, is just negative of the sum of the other entries in the row, right? And you can see that obviously from the first thing. So I have a star there, I have a 0 here, another star. These all turned into cosines. And then I have stars on my diagonal. And these are all going to turn into cosines. Okay, so so the question was, when we turn this into, or when we look at the all-in phase solutions, which is where the theta i's are all 0, what do we get? And of course, what we see is that these are all going to be 1s because these are all 0s. So what I get is a matrix that looks like, I'll put it down here, nice little 5 by 5 matrix. Can't see that. So this was supposed to be the second prize, but unfortunately I've already given it out. So the question was, who is this? Somebody else, any grad student or a postdoc can get a free whiskey. So this is the negative of the graph Laplacian. So the graph Laplacian is essentially, if you look at Newton's model for heat diffusing on a graph, right? So if I had little heat sources at these vertices, and these are connected by wires, and I want to solve the heat equation on this graph, you get exactly a system of differential equations where the matrix, it's a system of ODEs, and I have my derivatives down one side, and I have the graph Laplacian right here. So this is the graph Laplacian appears. This is the negative of it, but this application to heat diffusing on a graph, you see exactly the graph Laplacian. So, and the point is, the graph Laplacian is, well, the graph Laplacian itself, this is the negative of it. The graph Laplacian itself is, it has 1, 0 eigenvalue, and it's positive semi-definite, and so that exactly, in this case, is showing us that the all-in-phase solution for this is actually a linearly stable point. So for this particular toy example, the all-in-phase solution is good. Okay, but where we were going was we were going to translate this system of equations into our xi's and yi's. So I want to do that now on this same board. Let me stop and pause. So we are transitioning now to algebraic geometry. So everybody's good on this, right? Yeah, Jane.
Are you assuming the graph is connected?
Yes, absolutely. If the graphs aren't connected, the oscillators don't see each other. So it's like direct sum thing where you just partition things. The other assumption I'm making, I said simple. The other assumption we're going to make is that it's actually two connected. So there's no isolated vertices that only have an edge to one other thing, because if I have a vertex of valence 1, the behavior there is just totally influenced by the behavior of the vertex that it can see. So I want our graphs to be two connected also. All right, so.
Can I also ask something?
Yes.
So why do you go through, could you also go directly to trigonometric polynomial and therefore be directly?
You could. You could. We didn't do that. So the system of equations that we get here, I'm going to write this as F0, F1, F2, F3, and F4. And I'm just going to rewrite them here. So when we use our trigonometric, when we use the easy identities up here, this equation, give myself a little space here, this is just going to be y0 times y0 x2 plus y0 x3 plus y0 x4 minus x0 y2 minus x0 y3 minus x0 y4. So that's what this equation turns into. And I'm only going to do one other one. So the F1 equation is exactly the same as this, but replace 0 with 1. And then this equation right here, let's do this one. So for F3, we get y3 times y3 x0 plus y3 x1 minus x3 y0 minus x3 y1. And so we have this system of quadratic equations. And so the problem, it's not so easy to see from here, but because it's essentially a fact that because the Jacobian has rank n minus 1, one of these equations, just make it this one, it doesn't really matter, this is the sum of F0 through F3. And so there's a problem right away. And the problem is that we're working in two n variables. I have n equations for my circles. So I have these cylinders that are along just in two variables. But then I have n minus 1 equations here. And so the problem, let's go back and start doing stuff here. So the problem, yes?
I was going to question about the history. With this, is there like a mu star that's some kind of phase transition that says when you're going to sync or not?
That is a great question. So the question was, we had this upper limit that was something like 0.78, whereas if the connectivity was over 0.78, you synced. And we did, and there's an example, the canal Moison example was something like connectivity 0.68, where there were exotic solutions. And so so it seems, I don't know if this is written down anywhere, but it certainly seems to be folklore, but I think it is written down. I'll hunt down, if you email me, I'll find the reference. It seems to be 0.75 is the thinking, that 0.75 is the critical value. And that would be great. I would, but you could.
So below there existing.
Exactly, that's
below there exists graphs with exact
exactly.
solutions. Above there.
That's they say. That's right. Great question. I mean, I would love to be able to. I mean, when we started this project, we were hoping to either find graphs that had exotic solutions closer or come down from the top, but we ended up doing something rather different, but still rather satisfying, at least to me. Okay, so so problem. We have 2n minus 1 equations in 2n variables. We're never going to have zero-dimensional solutions, right? We have far too few equations. So but we can salvage something, and we can salvage a lot. So the first thing to observe is that these n equations are visibly a complete intersection. They involve completely different sets of variables. So complete intersection just means we have n. Each of these defines a hypersurface. You're a complete intersection exactly when each hypersurface that you add in chops the dimension of the solution space down by 1. So these are obviously complete intersection. But then we have to deal with these quadrics. And so that's what the rest of the talk is going to focus on, is these quadratic equations. And so the idea, though, is that we can just do something very simple. And this is, I mean, which is we can always set one of our angles to 0, right? We're going to just choose our system of coordinates. When I do that, when I choose to set one of my angles to 0, that sets that kills off 2 variables, and it kills off one of these equations. So if we just fix.
I see. So the one-dimensional space of solutions is a sort of
That's exactly right. So we fix a theta 0 to be 0, and now we're 2n minus 2 equations in 2n minus 2 variables. And so this is where, and so it's obvious here that we're going to have a finite number of solutions only if this is a complete intersection. So this is an easy observation. It's not even, you can't even call it
well,
it's an observation.
Only if?
No. So
I guess there exists a non-singular solution somewhere.
So actually what's going to happen is that we're going to do, so here's the look ahead of what's.
There are plane curves whose real points consist of points.
Yes, you're right. So that's absolutely right. And so most of what I'm going to be doing now is in the complex case, but if you show there's finite solutions in the complex case, you find the real case. So where we're going is going to be something that Jane touched on her talk, which was primary decomposition. And so the idea is going to be all the action, in some sense, well, the action is, the first thing to ask is, what's the behavior of this nice ideal generated by quadrics? And then once we understand that, we want to know how does that solution set here intersect with our little cylinders. So that's the idea. So now it's time for this is where sort of computational algebraic geometry enters the picture. So quick review. So I have to say I should compliment RUVIEW. I think almost every speaker really made an effort to review sort of some of the fundamental areas for them, but because we're such a broad audience, perhaps not fundamental areas for everyone. So I want to do a quick review of what's called primary decomposition, so which is bread and butter for PRIMARY decomposition, so bread and butter for someone trying to solve systems of polynomial equations. So the idea is that I is going to be an ideal in a polynomial ring, so I has what's called a primary decomposition. I has an intersection I equals 1 to some number m, finite, of QI. These are what are called primary ideals. I'm not going to write down the definition because for me it doesn't really matter. The point is that the radical of the QI is a PI, which is a prime ideal. And so if we're interested in the solution set, V of I, this is just going to be a union of V of PIs, where the PIs are what are called minimal And I want to draw a 2-second little picture over here to illustrate what's going on. So let's take an example 1. Let's say I1 is x squared xy. And I want to think of this as sitting inside k of x, y, z. Right? So the primary decomposition of this is simply x intersect x squared y. Visibly, this intersection is correct. It's easy to see because it's a monomial ideal. And the radical of this is just x. The radical of this is xy. Right? And so I'll just write those as the radical. If we think about the geometry of the solution set in 3 space, of course, this defines the plane where x is equal to 0. So here's my x coming in there. But then I have this line where x and y both vanish. So x vanishes, I'm in the plane, but my y-coordinate also vanishes. So this is this line sitting here. This is not a minimal prime, and it's exactly geometrically the fact that this line is sitting inside this plane. So this is a minimal prime, and this is what's called an embedded prime. All right, example 2. Yes?
Why it's not prime? Oh, I see. But actually, never.
So example 2 is I2, xy, and xz. So now this decomposes as x intersect y comma z. And the picture is much different because we, of course, have the plane. But now this line is this line, draw it punching through. So this line that punches through through the plane. So these are both minimal primes here, right? So these are both minimal primes. So the geometry, this is min, this is min. So that's the geometry. And so if we're interested in analyzing this variety, and I'm going to actually call this ideal, let's say IG is this ideal generated by F0 up through F sub n minus 1. I want to understand the geometry of this ideal, and what I want to do that is to understand the primary decomposition of this ideal. So this is the last bit of the talk. And so I want to do...
Hal, do you need a little bit bigger piece of chalk?
Thank you, Frank.
Well, thank Evelyn.
Thank you, Evelyn. Evelyn, thank you. I'd give you a whiskey, but you already earned one. Okay, so primary decomposition, this is the end. Primary decomposition, so this is part 4 results. Primary decomposition for this, the piece of the ideal that's the quadrants that just depend on the graph. So I'm going to write down, we have this for our example. The primary decomposition is the following. I'm going to just write it down. Let's see, here it is. And, okay, so the primary decomposition is IG is equal to P1 intersect P2 intersect P3. So it's pretty nice. There's 3 pieces. P1, P2, P3. This is given by 2 linear forms. And a quadric. This is given by 2 linear forms. And 2 quadrics. And this one is given by the 2 by 2 minors of the following matrix. So there's the primary decomposition. And so we did, you know, not millions, but certainly hundreds of examples. And the Segre variety, so this is defining, this defines V of P2, V of P3 is just equal to the Segre variety. Sigma 1 comma, in this case 1 comma 4, 1 comma 4, Segre variety. So Segre variety, in this case, if we take any Pn cross Pm, and we embed it into P to the n
n minus 1.
n minus 1.
N times n minus 1.
Yeah, n minus 1 and m minus 1 by using sort of, if this had S0.
Oh, it's worse. No, sorry.
It's n, wait, it's n plus 1. It's
long.
n plus 1 times m plus 1
Minus 1.
minus 1. Okay, S0 up through Sn cross T0 through Tn goes to basically you choose all the Si Tj's, right, in which there's this many, and you embed it that way, and you get a classical Italian, classical variety that appeared, hundreds of years ago, or at least 100 years ago, probably hundreds of years ago. And what happens is the Segre variety, this is always, so here's a theorem, harder to prove than one would expect. The Segre variety sigma is always a minimal prime of, or I sigma, I guess I should say, the ideal of I sub g, and all standard solutions lie on sigma. Now, the thing to note,
What do you mean by standard solution?
the standard solutions, they're gone now. Those were the solutions when my theta I minus theta j was either 0 or pi. So we have 2 to the n such simple solutions that are just caused by...
Did you call them stable?
No, stable just meant you were sucked back in. So, and all the standard solutions lie on sigma. I'm going to say just a tiny bit, if there's time, about the proof of this, because it's a good, Rhoda says, give me something to take home, and the take home, you're like, okay, you turn this into a system of algebraic equations. You're doing standards, sort of, standard computational algebraic geometry. Where's the trick? Where's my something to take home? There's a good trick that goes into this proof that I hadn't seen before that I liked. So I'm gonna that'll be at least part of the take home. Anyhow, so that's theorem 1. The other theorem that is kind of staring us in the face, which you don't see unless you look at sort of special things, is these things are things that in our graph. They kind of are jumping out at us, right? x0 and x1, these vertices somehow are similar. x2, x3, and x4 are somehow similar. And it turns out that in the study of Kuramoto systems that people had talked about twins. So twins, so vertices vi and vj are twins if they have the same set of adjacent vertices. So obviously, V2, V3, and V4 are twins. Right? They both have exactly the same set of adjacent vertices. So then, of course, x0 and x1 are also twins. So we wanted to find something, though, that's a little more special, so we'll call something a triplet. So Vi and Vj are going to be triplets if they share the same vertices, and the cardinality of that set is 3. So these are really twins, but we could also call them triplets because they share 3 vertices. Similarly, you could define, your life becomes more complicated when you have triplets or quadruplets and so on. And the second part of the theorem is if G has a set of k-lets with k greater than equal to 3, then IG has an associated prime of codimension less than or equal to, actually I should say less than or equal to k. So at this point, we have 10 minutes left. It's the last talk. And so all I want to do is talk about what this means in this particular instance. And the point is that there's a triplet. This ideal is visibly codimension 3, right? I got 2 linear forms and a quadric once the quadric was generated by these things. Because this has codimension 3, the associated affine variety is going to be a 7-dimensional thing, right? There's no possible way that I can cut down with my nice circle equations to have a zero-dimensional solution set on this component. And the point is that actually, if you go back, if you go back and think about what that means, it means that this is codimension 3, the tangent space to this thing, this is 7-dimensional. So affine, it's going to have a 7-dimensional tangent space. I can move on that tangent space because who is the tangent space? Well, the tangent space is the kernel of the Jacobian matrix, right? But the kernel of the Jacobian matrix, when I look at that kernel, having that positive dimensional tangent space means I have too many 0 eigenvalues, right? The Jacobian's going to drop rank. I have too many 0 eigenvalues. That means this cannot be a linearly stable solution. So it's a kind of a very nice interplay between these components that you get from some graph theoretic properties and forbidden solutions, right? So if you're trying to say, I want to find the solutions, if you do this decomposition, so you do a pre-processing step to your ideal that you got from the graph, you could find some of these components that are low codimension, and those components can't have solutions, so you could throw them out, right? So toss them out. And so that's the idea. On the other hand, we know that we always...
Not solution means that they're just not stable. If they're
linearly stable. That's it. Now, so Frank just made a great point. We were interested in linear stability. That turns into, this issue about the rank of the number of negative eigenvalues of the Jacobian. So they could still be stable. So
you're able to identify large sets of solutions that are just...
That's right. They're not going to be linearly stable, and so toss them. On the other hand, these two things, you can have solutions on those. So that's sort of the algebraic part. I wanted to say one last thing that has to do with numerical algebraic geometry. So John Hounstein and others started out using numerical algebraic geometry. So I haven't said anything about topology, and I want to just say in the last 7 minutes a little bit of topology. Eine kleine.
Can I
Yes.
ask a question?
Yeah.
So here you gave you kind of shifted from primary decomposition to prime decomposition. Huh? Here you
Yes, absolutely.
spoke upon the prime. Does the embedded primary component give you something interesting?
So actually it's a great question because this is the primary decomposition. So this is actually a radical ideal. So in this case, and in fact this is one I'm going to talk a little bit about future directions. It looks like in all the examples that we've seen, this ideal is always a radical ideal. So we don't have embedded components. But that's a conjecture for the future. So that was that. So the last thing I wanted to do was talk about topology. So we used, so there's a package which is not yet out, but it'll be in the next release of Macaulay 2 called Oscillators, where you can do all these sorts, all you do is input a graph. There's a really nice, there's a package called Naughty Graphs, which lets you do graph visualization. So all you do is, input a matrix of your edges, and you can visualize these graphs and then run all these sorts of computations and find solutions and look at your Jacobian matrix using numerical algebraic geometry. There's several different options you can use. You can use Bertini, for example, but there's other choices. So it lets you do that. And so what we did before we sort of did this piece of the project was to look at, and you can ask for isomorphism classes of graphs. So I can say, I want to see all isomorphism classes of graphs on 5 vertices, 6 vertices, 7 vertices, 8, continue down the list. Spits back a list of thousands of people. So how many isomorphism classes, let's say, n is the number of vertices, iso classes of graph. Okay? So, and these are the graphs that we're interested in. Simple, connected, and 2 connected. And it produces a list. So it's great if you're, I can't hype naughty graphs enough. It's really nice. So let's say n is 5, 6, 7, 8, 9. Let's start there. How many isomorphism classes of such graphs? There's 11, 61. Now, this is not a daunting number for us, right? Except that the problem is that in numerical algebraic geometry, even for, it really depends very much on the graph. And some graphs, like when you have the complete graph and you're trying to compute the Jacobian matrix, this really starts to slow down. But these are, I'm gonna talk about these 4 classes. And so how many graphs have exotic solutions? So here it is. That's the reason I didn't use this board, so I had hidden stuff. So on up to 7 vertices, so on 5 vertices, there's only one graph that has an exotic solution, which is a cycle. On 6 vertices, these 2 graphs have exotic solutions. And then on 7 vertices, we actually get 9 more things with exotic solutions. So for the last whiskey prize, I mean, you look at this and you think, okay, I know what a theorem is.
They're not chordal.
I think you can do better than that. Because I'm giving out the whiskey, I get to decide what the aesthetics of the answer. So that is not aesthetically pleasing to me. There's a better answer, I think. Because I would have included, if it was an issue of Quortal, I would have included this
I
guy.
understand, yeah.
But you're close.
They always have a pentagon, no?
Almost. Close.
Hexagons.
Is it a genus?
No.
I'm going to let...
Well, he also,
I'll let Frank and Evelyn split the prize because it's that they all have at least a chordless n cycle of n greater than or equal to 5, right? So
Oh, there's a 7 gon, okay.
yeah, they all have a chordless n cycle. We see 5 cycle, 6 cycle, 7 cycle, and then they all have big cycles. So you would think, so that was up to 7 vertices.
But, yeah.
So
That's not a characterization.
how about for 8 vertices? So it turns out this works for 8 vertices. There's something like 81. So we have 81 there's 81 graphs with exotic solutions.
It's pretty thin on the ground.
And they all have a chordless n cycle with n greater than 5. Except your theorem blows up in your face. Thank God for computations. Except for this guy or gal. So here's a little interesting thing that pops up. And back to the drawing board in terms of what the conjecture is. So this has an exotic solution, but it's obviously doesn't have a chordless 5 cycle. So that's a good place to end. I think I'm 2 minutes early, so thank you all for staying for the very last talk of the conference. I should really buy everybody a whiskey, but I'm not doing that. So, all right, thanks again.